Hi there, and thanks for tuning in today. I've been working on a project that's exploring how populations of the invasive Asian carps will perform in the Great Lakes under anticipated climate change. But today, I'm specifically going to discuss a model I've been developing for Bighead Carp, which is one of the species among the Asian carps. I'm Erik, by the way, a PhD student at the University of Toronto, Scarborough. So we'll start off with a quick background on the Asian carps. And then I'm going to discuss the problem I'm interested in, which is how invasion may interact with climate change. Then I'm going to share with you a model I'm developing to explore this question, how it was parameterized, and what outputs I've used it to produce so far. And then finally, some concluding statements. So around the world, there are several species known as Asian carps, but in North America, the Asian carps are comprised of these four fish species: the bighead carp, black carp, grass carp, and silver carp, which primarily prey on zooplankton, mollusks, macrophytes, and phytoplankton, respectively. These fishes are native to China and Russia, and they were first brought to the United States in the 1970s to serve as biocontrol on various pest species in highly eutrophied systems like sewage treatment lagoons and aquaculture facilities. The same characteristics of these fishes that make them so effective as pest control is exactly what makes them so dangerous as invasive species. They have a very large appetite and are fast growing, which helps them to reach sizes large enough to escape predation by native fishes. Additionally, they feed at a low trophic position, which affects many native species through disturbing the food web at its foundation. Bighead carp can reach a maximum size of 1.5 meters, which looks like this against a 6-foot tall person. And their range has expanded considerably across the United States. Americans are most concerned with their potential entry into the Great Lakes through Lake Michigan. But as Canadians, I think we should take note of these catch records here in Lake Erie, where 3 fish have been caught in the last 20 years. The first catch record in 1995 was for a relatively small fish, but then 2 considerably larger fish were caught in the year 2000, this one in June, and then this one in October. The main reason I'm paying attention to Lake Erie is because the Welland Canal, which connects Lake Erie to Lake Ontario, has already been identified as a potential breach point into the Canadian Great Lakes by another Asian carp, the grass carp. There have been records of bighead carp caught close by in northern Ohio as recent as 2 years ago. So how serious would the consequences be if a bighead carp were to manage to have a successful reproduction event around the Welland Canal in the near future? Further, would climate change exacerbate the outcome? Under unmitigated climate change, by the year 2080, the region surrounding the Welland Canal is projected to have a climate similar to that of Arkansas, where bighead carp are highly abundant. Now, in warmer conditions, we know that fishes can grow faster and reach larger body sizes, which make for an increased rate of survival. However, life history theory tells us under warmer conditions, ectotherms mature earlier in life, which means that they will obtain a smaller adult body size. This is because energy is primarily allocated to gonadal maintenance over somatic growth after reaching sexual maturity. For females, this smaller adult body size comes with a reduced fecundity, as large female fishes are known to have a disproportionately larger reproductive capacity. And this is something that appears to be happening with bighead carp around the world. There are various records that show bighead carp are maturing at a later age at higher latitudes, while at lower, warmer latitudes, they are maturing earlier in life. Looking elsewhere in the world at the latitude of the Welland Canal, we can see the average age of maturity is around 6 years of age. But then looking at the latitude of Arkansas, it appears the average age of maturity is closer to 3 years. So under climate change, can we expect a 3-year reduction in the time to maturity for bighead carp? The questions I'm currently looking to explore is how will warming affect the population structure of bighead carp? Will climate change result in earlier maturity? And will that give them some kind of advantage? Climate change, of course, doesn't just mean a shifting mean temperature, but also changes in variability. So I'm also interested in the effects that increased variability might have. Previous bighead carp population models have examined separate scenarios with various fixed ages of maturity, which would assume all adult individuals have similar characteristics. But I wanted to explore what might happen if, under a changing climate, individuals would mature earlier or later in life, resulting in differences in their associated fecundities or survival rates. For instance, individuals in colder environments that had to risk mortality for a greater length of time before they gained the chance to reproduce are, in a sense, rewarded with a larger body size and greater fecundity. To address this, I created a stage-based model where juvenile bighead carp can spend a variable amount of time as subadults before maturation, depending on the environmental temperatures they experience. Given that bighead carp mature at 6 years of age elsewhere at the latitude of the Welland Canal, this was set as the maximum age of maturity for the model. Mathematically, the model is a mix between Leslie and Lefkowitz matrices because it's structured by both age and life stage. There are primarily two types of parameters in this model: age of maturity and survival, which differ for each individual life stage as a function of temperature. Lastly, there are fixed fecundity values for each adult age class, which are drawn from the literature. Adults that are matured later in life at a greater size have larger fecundity values. Just like how maturity occurs sooner at lower latitudes, we can see that growth is also faster. I compiled a dataset of length at age for bighead carp in various locations in the world, and then I retrieved the annual temperatures with the winter months removed for the corresponding locations for each of the data points. Next, I fit regressions for length versus temperature for ages 1 to 6. Temperatures from the winter months were not included because they contained values too cold to realistically include as a proxy for water temperatures. The length to temperature functions were used in conjunction with two other functions to calculate survival for each life stage. Length was converted into weight using a relationship from another bighead carp population model, and then the weight values would be used to determine the probability of survival based on Lorenzen's natural mortality relationships for juvenile and adult fishes. Since my model involves a subadult class, I derived a third natural mortality function that's simply the average between the published juvenile and adult functions. To parameterize maturation, I compiled the ages of maturity for bighead carp in various locations around the world and fit maturity against annual temperatures, again, with winter months removed. This relationship was used to create a function that would determine the ratio of subadults that would reach maturity at each year of life as a function of the temperature. As subadults age, there is an increasing likelihood that they will mature, even at lower temperatures. In order to mature early in life, however, higher temperatures are necessary. The non-winter annual temperatures for each of these locations was obtained through hindcasting historical values from the R1I1PI ensemble of general circulation models and taking the mean value from all model outputs. I did this for congruency's sake, as I would then use the same ensemble of models to produce the climate projections for the Welland Canal under various scenarios until the year 2070. I ran simulations with my model that explored population performance after a single reproduction event. I considered a combination of 3 different representative concentration pathway, or RCP, climate change scenarios, 5 different temperature variability scenarios, and 5 different founder scenarios, which involved bighead carp of varying fecundity values from different adult age classes. This was used to determine the influence that these conditions would have on the time to establishment, which has been defined elsewhere as when the population contains 1,000 or more female individuals. Scenarios would begin with a single reproduction event from an adult that matured between 2 and 6 years of age, with temperatures gradually increasing from the historical average temperature for the Welland Canal and ending at the temperature projected under either RCP 4.5, 6.0, or 8.5 scenarios. Lastly, depending on the temperature variability scenario, the temperatures at each year would randomly vary between 1 and 5 degrees above or below what was predicted for that year. Altogether, 75 unique combinations of scenarios were examined, and each were ran for 100 simulations to get a reasonable distribution of outcomes. What I found was that the projected temperatures used in this model were insufficient to prompt maturation earlier than age 6 for the most part. Only in scenarios with the greatest degree of warming and the highest temperature variability were there instances where maturation occurred earlier, only at 5 years of age. Accordingly, population structure did not change significantly under climate change in the Welland Canal, according to this model. We can also see that climate change of greater severity, like that of RCP 8.5 versus 4.5, does not result in establishment occurring sooner. All RCP scenarios have the same median time to establishment. and the same is true for increasing temperature variability. Greater temperature variability produced more simulations where establishment did not occur at the median value. Some simulations did result in establishment occurring earlier than the median value of 23 years here, but it was more often the case that establishment was delayed than advanced. What did have an effect, however, was the fecundity of the founding individual. An A2 adult, meaning an adult which matured at age 2, could produce an established population in 23 years on average, but an A3 adult could do it a year sooner, while an A4 individual could do the same in 16 years. At this point, the median time to establishment no longer changes with increasing fecundity, as simulations with A5 and A6 founding individuals produce the same result. I did some additional exploration which subjected the model to temperatures sufficient to induce earlier maturation to determine the effect it would have if it were to occur. Using an A2 founder and RCP scenario 6.0, I found that establishment would occur sooner if there was maturation before age 6. For each year of earlier maturity, establishment would occur 2 to 3 years sooner, with establishment occurring in as few as 14 years on average if Bighead Carp could mature by age 2. In conclusion, the environmental conditions necessary to prompt early maturation are not expected to occur in the Welland Canal by the year 2070. That said, we can see that earlier maturation would result in earlier establishment if it were to occur. But the most pronounced effect on time to establishment is the age class and fecundity of the individual that started the population. And with that, I'd like to thank all the various people and institutions that have supported me in my work, and also to you, the viewer, for your attention. Thank you.